So we've seen Taylor polynomials, which give us a way to approximate a function with a polynomial. And today we're going to take a look at Taylor's theorem, which takes a look at estimating the accuracy of our approximation, determining an upper bound on that remainder. Okay, so Taylor polynomials estimate the value of a function because the polynomial approximates the function at least over some interval. And the next logical thing we would ask ourselves is how accurate is our approximation? All right, so if we use a polynomial to estimate the value of a function, the approximation is going to be off by some amount. That amount that we're off by is called the remainder. And we're going to find a way to estimate that remainder, come up with an upper bound of that value. So the true value of the function f of x is equal to the estimate, the polynomial, plus the remainder. So here's Taylor's theorem with the remainder. So you can see that we're just saying here that the function f of x is equal to the Taylor polynomial out to degree n plus the remainder after degree n. So we use the notation r sub n. So adding that extra piece there turns this into an equality, meaning both sides are exactly the same because we have that amount, that difference between the two added on there. And that remainder is actually equal to what's essentially the next term in the Taylor polynomial, except if you notice here that derivative, that n plus 1 derivative, is evaluated at some number c. Now, we have a polynomial that's centered at a. C is just some number between a, where we're centered, and x, the value that we're approximating this at. C is just some number in there. The only problem is we don't know what that value is. Okay, so as far as understanding how to calculate this, just realize that this is the next term in the polynomial, with the exception, like I was saying previously, that a is replaced with c up there in that derivative. Now, this can still help us even though we don't know the value of c, because we know that c is between x and a. So if we just choose whatever number within that interval makes that derivative the biggest, we can put an upper bound on this remainder. So let's call the max value of that derivative m. So if we make everything positive, so we're just going to deal with absolute values here, the absolute value of the remainder is less than or equal to m over n plus 1 factorial x minus a to the n plus 1. So we just replace that derivative with the largest value that it will take over that interval, and then we can go ahead and come up with an upper bound for the remainder. And we call this Taylor's inequality. In our textbook, there's a slightly different formula given, but it overcomplicates it more than we need to. This formula right here will do everything that we need it to do. Okay, so we're going to take a look at sine of 0.1. We want to approximate that using this polynomial here. So we've got the degree 3 polynomial, and then we want to figure out how accurate that approximation actually is. So first we can say that sine of 0.1 is approximately equal to 0.1 minus 0.1 cubed over 3 factorial. And we could theoretically figure this out by hand, but we'll just punch that into the calculator because we can, and we get an approximation of 0.099833. And now we want to know how accurate is this? Well, we've gone out to degree 3, which means if we constructed this polynomial, we have used the third derivative. So if we want to come up with an upper bound on that remainder, we need to take a look at the fourth derivative. So we've got our original function, first derivative, second derivative, third, and fourth. And sine of x, we know that values of sine of x go between -1 and +1, so the max value of the fourth derivative is 1. All right, so now we have our inequality for the remainder. The remainder, when we evaluate sine at 0.1, is less than or equal to the max value of the fourth derivative, which is 1, divided by 4 factorial, because we had a polynomial of degree 3, times, now we have this piece here, x minus 0. It's minus 0 because this is a Maclaurin polynomial. It's centered at 0. And 0.1 because our interval goes from 0 to 0.1, and we want to plug in whatever number from that interval is going to make this thing the biggest, which would be 0.1. And then to the power of 4, again, because we had a degree 3 polynomial, and we increase n by 1 for the remainder. And if we crunch those numbers, we end up with 0.000004. So we know that our approximation of 0.099833 is off by no more than 0.000004. And so if we add and subtract that remainder, we know that the true value of sine of 0.1 is somewhere between 0.099829 and 0.099837. So depending on for what purposes you need this approximation, that looks like it's a pretty good approximation. Okay, so we want to find the error bound when we use the degree 2 polynomial x minus x squared over 2 to approximate natural log of 1 plus x for values of x that are between negative 0.1 and positive 0.1. So we have our interval from negative 0.1 to positive 0.1. We could use any of those numbers, plug it into that polynomial to come up with our approximation for natural log of 1 plus x. We want to figure out for all of those approximations, what's the most that we're off by. Okay, well, we know that to come up with this remainder inequality, we need to go out to the third derivative. So we take the first, the second, and the third. And we need to figure out when that's the largest, because we're trying to find the max value of that next derivative, in this case, the third derivative. Well, that's 2 over 1 plus x cubed. We know this is going to be the largest when the denominator is the smallest. So that's when x equals negative 0.1. So the max value is 2 over 1 minus 0.1 cubed. And if we crunch those numbers, we would get that in decimal form right there. Okay, so now let's go ahead and see if we can come up with an upper bound for the remainder. All right, so we have our value of m. We can put that into the formula. We have this x minus a. Well, again, we have a Maclaurin polynomial, so a is 0. The value we plug in for x is whatever number in that interval is going to make that portion of the remainder formula the largest. So that would be 0.1. And then we can crunch those numbers, and we get a remainder less than or equal to 0.000457. And we call that our Lagrange error bound. So let's take a look at this. Now that we know how the largest that remainder could be, let's go ahead and confirm that that's actually true. So let's take a look at when x is 0.1. The original function, natural log of 1 plus x, that would be natural log of 1.1, gives us 0.0953102. And if we use the polynomial, which approximates natural log of 1 plus x, we get 0.095 for an error of 0.000310, which is less than the error bound we got of 0.000457. So that confirms to us that upper bound we came up with really does appear to be an upper bound. And let's take a look at negative 0.1. That would be natural log of 1 minus 0.1, or natural log of 0.9. Plug that into the polynomial. You can see that those are very close. They're off by 0.000361, again, less than our Lagrange error bound. So let's take a look at cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. So we have our Taylor polynomial approximation for cosine of x. This polynomial has 3 terms because there are 3 individual pieces being added or subtracted. It's a 4th order polynomial because it was found using the 4th derivative. It's a 4th degree polynomial because it has degree 4 of 4th power. But it also could be considered a 5th order Taylor polynomial because the order refers to how many derivatives you take to construct the polynomial. And if we went out and took the 5th derivative, well, that next term would just drop off because the derivative would be 0. So even though it's of degree 4, it could be considered 4th order, or it could be considered 5th order because both would create the same polynomial.